I'll note that there is actually a shortcut for computing these Seifert surfaces and their classifications without going through this process every single time. And we present this shortcut in the following proposition. Okay, so the shortcut is this. We take some Seifert surface S with n crossings and m Seifert cycles, and then S prime, and recall that S prime is the resulting surface from gluing disks to the boundary of S. That's a closed surface. So S prime is topologically equivalent to mg, where g, the genus, is 1 minus m plus n over 2. This is a pretty interesting result, but it's actually not too hard to prove, and the proof is basically a more general version of the process we just completed for the trefoil Seifert surface. So for simplicity's sake, we're just going to address the case when S is a Seifert surface that has a knot as its boundary, as opposed to an arbitrary length. Okay, so to begin, let's observe that S is always orientable, as a Seifert surface is orientable by definition. Thus, when we adjoin orientable disks to the boundary of S, we obtain another orientable surface. And so S prime, then, is orientable, meaning that S prime falls under mg as opposed to nk. So in other words, S prime is topologically equivalent to mg for some genus G. Okay, great. Now let's try to compute what this genus is. To start, we're basically going to compute the Euler characteristic just as we did in the case of the trefoil Seifert surface. Right, so if you recall, the way that I did this is first I placed vertices 4 at each crossing. And in general, this is actually what you do. So you place 4 vertices at each crossing, giving us that V of S is equal to 4n. Excellent. Before addressing the edges of this surface S, we see that the faces come from each of the Seifert circles is one face, so M. And then each of the crossings gives us a half twist, which is just a square face. So we have to count those as well. Faces are M plus N. Finally, edges. Well, where do edges come from? Notice that for an arbitrary Seifert cycle that I'll draw here, when we add in a half twist, we basically create 3 edges where we originally had only 1. And so in that sense, each half twist contributes 2 edges to each Seifert circle that it's attached to. And remember that each half twist is in fact connected to 2 Seifert cycles. And so this gives us that we have 2 edges over here and 2 edges over here, giving us a total of 4 edges that each half twist contributes. However, we're not done counting, as each half twist actually has 2 edges of its own, which I'll show you right here. So we count those as well. And that gives us that that the number of edges is 6 times the number of crossings. So with this information, we can compute the Euler characteristic of S, which is simply 4n minus 6n plus m plus n, which is equal to m minus n. Excellent. Now I'm going to erase this to give myself a little bit more space. Now we're basically halfway there. With the knowledge of the Euler characteristic of S, it's pretty easy to compute the Euler characteristic of S prime. So basically, Euler characteristic of S prime, based on the formula, is Euler characteristic of S plus chi of D, the disk, minus chi of S intersect D. And the Euler characteristic of a disk is always 1. The Euler characteristic of a circle is always 0. And thus, chi of S prime is equal to chi of S plus 1, which in this case is m minus n plus 1. Okay, so now we're almost there. And to finish the job, we are going to present the following formula, which is that the genus is equal to negative chi over 2 plus 1. And this is really not too hard to show. For example, If chi equals 0, then the genus is 0 over 2 plus 1 equals 1, and we have a one-hole torus. Right, so in this case, our genus is negative m minus n plus 1 over 2 plus, say, 2 over 2, which gives us that G is, in fact, equal to 1 minus m plus n over 2. And that's the proof. Okay, and now we can use this shortcut to verify our answer for the trefoil knot. So the trefoil knot has 2 Seifert cycles, n equals 2, and it has 3 crossings, n equals 3, and thus our genus is 1 minus 2 plus 3 all over 2, which is in fact equal to 1, which is what we want. The S prime is a one-hole torus.